Welcome to today's video. Today we'll be looking at the single number algorithm. A very simple algorithm we're looking at. Hopefully we can learn one or two things. This algorithm series I'm going through is from the Sin Prashad lead code patterns. I have been dropping in the description. It's only going to be in the description of this video. You can go through it and see the hierarchy. I am going through it by difficulty, so you could go through maybe by companies or by some particular patterns, but I'll be going through by difficulty. We have done the first, second, and third, and today we are going to the single number. If you like this kind of videos on algorithms, or you're preparing for an interview in the next few months, I think this series will be helpful to you. Thank you. So, the single number algorithm, the question goes that given a non-empty array of integers nums, every element appears twice except for one, and we have to find that single one. They say we must implement it in linear complexity and in constant extra space. So it means the time complexity must be O of n, and the space complexity must be O of 1. Now, so let's look at this, the examples we have. So we are given 2, 2, and 1, and the answer is 1 because 2 appears twice, but 1 appears only one time. The second, we have 4, 1, 2, 1, 2, and 4 is the answer because 1 appears twice, 2 appears twice, and 4 appears only one time. And yet, since it's just 1, of course, 1 appears only one time. So they say each element in the array appears twice except for one which appears once. So all will definitely appear twice. So it's important we take note of this, except one. So let's look at what approach we could use to solve this. So we are given nums to be an array. Let's use something 6, 4, 3, 4, 2, 3, 2. So in this, we know that the answer is going to be 6 because 4 appears twice, 3 appears twice, 2 appears twice. So the first approach coming off my mind, it will be a dictionary. So we could have a dictionary which will be empty at the beginning, and we go through it. So we can, when we go through it at the first point, when we are 6, we know that 6 appears one times. When we get to the next item, it becomes that 6 appears one time and 4 appears one time also. The next iteration, 6, we have 6, 4, and 1 has appeared one time. 3 also appeared one time. When we're in the next iteration, that we are at 4, 4 has appeared already. So at this point, I know that 4 has appeared 2, so I increment that to 2. 3 is still appearing just one time. When we go to the next item, that is 2, 2 is just appearing for the first time. So 6 will have appeared one time, 4 will have appeared 2 times, 3 will have appeared one time, and 2 will have appeared one time. We go to the next, which is 3. 3 will make it 6 appearing one time, 4 appearing 2 times, 3 appearing 2 times, and 2 appearing one time. And then lastly, we look at the last number there, which is 2. So 6 appears one time, 4 appears 2 times, 3 appears 2 times, and then 2 appears 2 times. So that will be our dictionary at the end of the day. So what we can now do is to go through our dictionary, and then in our dictionary we're checking and asking which of these items appeared only one time. So as our dictionary shows, we have 6 appearing one time, 4 appearing 2 times, 3 appearing 2 times, and 2 appearing 2 times. So here we know that definitely, so if we are to go through this, when we get to 6 and we see 6, we see that 6 appears only one time. So we know that based on that, that the answer is definitely 6. So our answer will be, we return 6 as the answer. So that is the first approach we use. But we see with this, we are going through this, the time complexity of n, because we are just going one time. But also the size of our dictionary will also be O of n over 2. And n over 2, which is still n, because we know, if for example we know that all the values will be double except one. So that's why I say approximately is going to be n over 2, which in O of n is still going to be an O of n, because the input size increases with this with the size. I mean, the size of our dictionary increases with the size of the input. So our time complexity for this is O of n, and our space complexity will still be O of n. But you know, if we look at the instruction, we are told that it is to be done in a constant extra space. So let's go back and see how can we achieve this. So let's just go to, okay. All right, so let's now come back again and try seeing what. So we have norms, and we have our array 6, 4, 3. I think we had 4, 2, 3, 2, something like this. And we want this to be in constant time. Now, so there is this bit operation, which we know in truth table we have for and. When we have and, if we have 1 and 0, let me just put this. If we have 1 and 0, so 1 and 0 will be 0. 1 and 1 will be 1. 0 and 1 will be 0. And 0 and 0 is 0. This is for and. For or, we have that 1 and or 1 is 1. 0 or 1 is 1. 1 or 0 is 1. And then 0 or 0 is 0. So meaning that for and, it's that if we have, the only point we have a true is when both situations are true, taking this as true or false, one being true and 0 being false. So for and, it is that the two statements must be true for the overall statement to be true. But for or, it's that any of the statements could be true for the overall statement to be true. If both are false, it's going to be false. But we have one we call XOR. In XOR, we have that let's have 1 1 1 0 0 1 and 0 0. For XOR, it is that when we have the same values, so for example 1 1, it gives us 0. But when we have different values, we have 1. So for example, 0 0 give us 0, 1 1 will give us 0. But when the bits are different, when we have true false or false true, we get a true, we get a 1 in that situation. So it means that if we look at 1 1, it means that it's as though they are cancelling out. So it's like as though 1 is cancelling out 1 to give us nothing, and 0 cancels out 0 to give us nothing. But when they are not the same, we have a value there. So we could use this XOR principle. So for example, since I know that every number we repeat, so for example, we have 6, we have 4, we have 3, we have another 4, we have 2, we have another 3, and we have another 2. These 2 can cancel these 2, these 3 can cancel these 3, this 4 can cancel this 4, and we know what we are left with is 6. So if we have a way to cancel them out, it will make sense to use that, since we will end up with only what is left that is not repeated. And that is where the XOR comes in, because 4 XOR of 4 will be 0. 3 XOR of 3 will also be 0. And 2 XOR of 2 will also be 0. And then we are just left with 6 as our answer there. So that is the second approach we could use, which will make sense. So what I will just be doing is trying to look for a way for them to cancel out each other. So if you want to see 4 is 1 0 0, and 4 is 1 0, so if you have 1 0 0, so and we have an XOR here, 0 XOR 0 is 0, 0 XOR 0 is 0, 1 XOR 1 is 0, and you see it cancels out, everything becomes a 0. And then so this will also be 0, this will also be 0, and then we are left with 6 in our array as the answer. So that is the approach we'll be trying to use. So we have our array to be norms, and we want to go through our norms, and we want to be what we want to be doing is we want to use the XOR operator to solve this. So first off is that I could just have a number, So let's just start with the first number, or we could start with 0, whichever whichever one is okay with us. So, and we can go through each, and so we can say for each norm in norms. And what we want to do is that we are saying that the number, and this is the XOR operator. So you could, this is the XOR operator here, or C sharp. This is what the XOR operator looks like. So this XOR of what we are currently at now. So for example, what we are saying here is that, so it was, so let's go back to this and look at it again. So we have 6, 4, 3, 4, 2, 3, and 2. So we are starting with 0. So 0x or 6 will not cancel out for it exactly. So we still have 6 here. 6x or 4 will still not cancel out. So we have 6 and 4 combined together there. You could use the bit operator. For example, 6 is 1, 1, 0, 4 is 1, 0, 0. And if you do an XOR for this XOR this is 0. Since these are different, so this is going to be 1 and this is going to be 0. So that will be like 2 will be the XOR. But basically, it still keeps going. So this is a XOR combination. So this 2 is an XOR combination of 6 and 4. So basically, 6 and 4, it's not been cancelled out. 4x or 3, so 3 combined, so we still have 6, 4, and 3 combining together. But when we do that with 4 again, the x of 4 here, we cancel the previous 4 that we have had. So that 4, we cancel out this 4. That's basically what we're doing. So when we get to 2 XOR, so it adds it up to the XOR. And 3, when we have our 3, we cancel out this other 3 that was there. And then when we have our 2, the 2, we cancel out this 2. And then what we are left with will be 6. So basically, if we look at this, so if all we just need to do at this point is just to return the number, because at this point, for each iteration, it will be compounding them. So for example, so if we could just show this with a smaller sample space, so let's say we have 1, 1, 2 as what we have here. So let me just create some space here. Oh, sorry. Let me close that. So we just move this here. Okay, so let's say we have a smaller sample space so that we can easily understand that. So I could just use, so let's say we have 1, 2, and 1. So 1 is in binary is 1, and 2 is 1, 0. So 1 is this. So when we do X of this, we have this is 1, this is 1, because they are different values. So this we now XOR the next one, which is XOR 1. So XOR 1 again. This is 1 XOR 1 is 0. 1 XOR 0 is 1. Now 1, 0 in binary is equals to 2 in number. And you see our answer is 2, because that is actually, so what actually happened behind the scenes is that this X and cancel out, the XOR cancels, makes this ones to cancel out each other, and so we're left with basically. So basically that's why we have this. And then when we run this, we should get, let's see. Okay, it passed all of them, and then when we submit, let's see if it is efficient, and it passed all cases, and it does. So this is how we can go about solving this particular algorithm. It's very simple when you understand the concept. So wherever you have repetitions that occur in even number of times, it's possible to cancel out with XOR. I hope this video will be able to learn and understand how to apply the XOR operator and how it can be utilized in our algorithms. If you like this kind of video, please subscribe, like, and watch. See you in the next video. Thank you.